Welcome, students. We are discussing the chain rule today with respect to our three space. In this, we have the derivative of some function z. Note that z is dependent on both x and y, and t is our independent variable. This would tell us that we will need to take the partial of z with respect to x multiplied by the straight derivative of x with respect to t, add that with the partial of z with respect to y times the derivative of just the straight y with respect to t. So let's see if we can do this. We need the derivative of z with respect to t. So I'm going to find the partial of z with respect to x. That would just give me 2x, the rest are zeros, times the derivative of x with respect to t. That would be negative 2 sine t. Add to that the derivative of z with respect to y. That's going to be negative 6y times the derivative of y with respect to t. So that is going to be 2 cosine t. Now what I'm going to do is I'm going to replace my x and my y with their respective equations, and I'll write that down. And this is what we get. We could use our double angle formula if you want to make that a little prettier. We're not asked to do that because we're asked to evaluate it at t equal to pi over 4, so I'm going to do that. I'm going to replace pi over 4, the t with the pi over 4 on each of those. Alright, doing my little computation, I get negative 16 as that value. Next they want me to interpret the result geometrically, so let's look at the x and y. That would be a circle of radius 2. Z would be my elevation, so I can only, if I'm looking at this saddle here, I would only be able to walk in this circle of radius 2, but I could do this with this elevation change, x squared minus 3y squared plus 20, and that's what that represents. But the boundary of my elevation in the xy direction is that circle of radius 2, and then the z gives reference to my elevation, or how high that I am over that circle. Next we're going to take the derivative of z with respect to s, where we have two independent variables, both this s and t. So notice that x and y are both functions of s and t. So let's play this game. So I want the partial of z with respect to s. That tells me I'm going to take the partial of z with respect to x first. Treat everything else as a constant, so the partial of z with respect to x would be 2 cosine 2x times cosine 3y. Then I would take the partial of x with respect to s, and that's just going to be a 1. Alright, I'll leave that one out. Partial of z with respect to y, meaning that that part right there will just be a constant, so I'll write sine 2x. Now I need the partial of y. That's going to be negative 3, and then that would be sine of 3y. And multiply by the partial of y with respect to s. That's going to be a 1. So this thing is then just, oh, well, he just kind of sits there like he is. Alright. If I would like to put this in terms of s and t, I would rewrite as 2 cosine of 2 times s plus t, and just replacing these x and y's with their respective equations. I'll write that down. Alright, let's do the other one. I need the partial of z with respect to t, and that is going to be the partial of z with respect to x. I think I already did that one. That is 2 cosine 2x cosine 3y. Now I need the partial of x with respect to t. Oh, that's a 1. Okay, so that stays. Plus the partial of z with respect to y. That's the same as what I had before because I'm doing the same thing again. So that's negative 3 sine 2x sine 3y. Now I need the partial of y with respect to t, and that would be, this is not the same, this would be a negative 1. Alright, so writing these down. Alright, all I had to do is just the negative times negative is a positive. I'm going to replace the x and y with the s and t so I can see this function of z, this function z with my s and t independent variables. Alright, and there it is. Alright, on to the next one. I'm going to draw a tree diagram to show the relationship for these variables. We are going to have our w at the top. So I'm going to write my w at the top. He is a function of both x, y, and z. Alright, so I wrote out what they've given me. So this is going to be the partial of w with respect to x. This is going to be the partial of x with respect to s, partial of x with respect to t, and I'm going to write all of those in. Alright, let's put this together. We need the partial of w with respect to s. So this is going to give us the partial of w with respect to x times partial of x with respect to s. Add with that, just walking down the tree here, I'll write all of those down. And there we've used the tree to come up with the formula for the partial of w with respect to s. You just walk down those branches and add up each of those different limbs. Alright, they want me to write down a tree where w is a function of z is a function of x and y are each a function of t. And I'm to come up with the derivative of w with respect to t. Alright, since w is a function of z, I can take the regular derivative of w with respect to z. Now z is a function of both x and y, so this will need to be a partial. It will be the partial of z with respect to x and the partial of z with respect to y. X is only a function of t here, so I can take the derivative of x with respect to t, and likewise over here. And now I'm just going to put all of that together. The derivative of w with respect to t is going to be equal to, and I'm just going to follow each of these limbs, adding together derivative of w with respect to z times partial of z with respect to x times derivative of x with respect to t, add to it the other limb. Alright, now that I have all of these written down, this would be how I would find the derivative of w with respect to t. Our theorem for implicit differentiation tells us if we want the derivative of y with respect to x, we are to compute the partial derivative of f with respect to x over the partial derivative of f with respect to y, and we would take the negative of that. So let's compute the partial derivative of f with respect to x. That means that I treat y as a constant here. So this would be, I'm going to take the derivative of sine xy, where y is treated as a constant. So that would be derivative of the outside, that would be the cosine, leave the inside alone, times the derivative of the inside with y being treated as a constant, that would just be y cosine xy. This guy would be a 0 because he would just be a constant, minus 1, and that is the derivative of f with respect to x, that partial. Now I'm going to take the derivative of f with respect to y, treating x as a constant, and that would be the partial derivative. This would once again be cosine xy, but this time x is the constant, so he would, when I take the derivative of the inside, that's where what I would get there, plus 2 pi y, and that would be a 0. Putting this together, dy over dx equals negative, and then just plop all of this stuff down. Alright, just plugging in those different partials and then making so I don't have the negative out front. There's what I get. Alright, in this problem they want me to find the partial of s with respect to x. So I've gone ahead and drawn out my tree so that I can follow my limbs down to get to that x and adding those together. So what I'm going to need to do is find my s wherever he happens to be. Oh, there he is. So there's my s, and I'm going to take the partial of him with respect to u, and then I'm going to look at my u equation and find the partial of that with respect to x, and then likewise I'll also do the same thing for v. Okay, this s function is a little messy. It might be easier to look at this x function as s squared equals u squared plus v squared, and then because I would like to find this guy first, what I'll do is take the derivative of both sides with respect to u, so that would be 2s with respect to u. This would be just plain old 2u, and you'd be 0. And rewriting for this one, I would get partial of s with respect to u equals u over s, because the 2's cancel out there. So next I'll write in that this is u over s. Then I will take the derivative of u with respect to x, and I can do that here, treating the y as a constant. That is going to be, it looks like 2 pi cosine pi x, and then just times that cosine pi y. And then plus, I'm going to do a similar thing with the v, and I would still get the very similar answer. I'm going to get the partial of s with respect to v is going to be v over s in this case, if you do that same set of computation. So this one's going to be v over s, and then I'm going to take the partial of v with respect to s with respect to x and write that down. Alright, it seems though no matter what I do, it's going to be pretty ugly. I can write it as 2 pi over s, because both of them have that in there, and then write the rest as I factor that out. Yeah, it's ugly. Okay, so I'm going to write down a similar thing for the partial of s with respect to y. Alright, that's just stunning. I'm going to factor out a negative 2 pi over s and get another mess of something. Okay, there's the equation for the change of the rate of change of the water speed in both the x and the y directions. Lovely. And if you guys have any questions, see me at the Collaborate. That concludes 13.5.